Today's lesson is over compound inequalities, which are a little bit different than the inequalities we've been practicing. I think up until now, most of what we've been doing is review, and you've had some exposure to it, but this might be the first time that you really get to discuss compound inequalities and the different kinds that there are and how we interpret those solutions. So let's go ahead and define what we mean when we say compound inequalities. So a compound inequality, go ahead and write that down. Okay. A compound inequality is an inequality that is formed when you join two inequalities with the word and or the word or. Okay. So there's two different kinds. There's the type of statement where we say there's these two inequalities that one and the other has to be true. And then the other type is where we have an inequality and we say this or this must be true. Okay. So the graph of a compound inequality that contains the and statement is going to be the intersection of the graphs of the two separate inequalities. Okay, so it's basically where they overlap. So think about that as the overlap. So that's what we mean by that. Okay, where do the two inequalities overlap? The graph shows the numbers that are solutions in both. So when it's an and statement, we only want, like in our final solution, we want the solution only, to be only the section where both inequalities are true. So we have a little example right here, and I'm going to use a little bit of color here since we lost color when we print. But essentially, if you look at this example, if we were just graphing all of the x's that were greater than or equal to 2, we know that we would put a filled in circle here with the 2 right there, and then we would get everything greater than. So if we had color copying here, that's what that would look like. And then we have another inequality that says, hey, I want all the x's that are less than 5. So we would have an open circle at 5, which is over here, and I would want everything less than. So then I can create a compound inequality that says, well, I want actually just the numbers that make both of these things true. I want to sort of narrow this down to the numbers where x is greater than or equal to x and also less than 5. Okay, and we can say that either with an and statement, or what you'll see very commonly done is they'll put that together as like a double inequality like this, and that only happens with the and statement. And so in the and statement, we might use the word, or we might say all the x's between 2 and 5 that include the 2 but do not include the 5, right? So basically we're looking at just this little section in the middle where the two solutions overlapped. And so my final solution for this and statement would be essentially just this section. Okay, that's where they overlap or where it is true for both. So all of the numbers here that I finalized in pink are greater than or equal to 2 and also less than 5. So it's everything in between. Okay. Now let's contrast that with the or statement. So the graph of a compound inequality that has the or statement is simply the union. Okay, it's just all of the answers that work in either one. Okay, so the graph shows the numbers that are solutions in either inequality. Sometimes we don't need to narrow it down to just where it's true for both. Sometimes as long as it's true for one or the other, we're okay. And so you have a great example of that here. If I wanted all the y's that were less than or equal to -2 here, I would put a filled in circle here for -2. I would shade to the left. If I wanted all the y's that were greater than 1, I would leave my open circle there, shade to the right. But if I want the compound inequality that shows me all of the solutions that are either less than or equal to -2 or y greater than -1, then it's basically the two, anything that makes either one true. So as long as it makes either this guy true or this one true, it's a solution. Okay? And so it does not have to overlap. Sometimes it will, sometimes it won't. But we just want every number that's a solution to at least one or the other. Okay? That is in either one. I don't need to narrow it down to just the overlap. And that's a big difference. Now, a lot of times in an and statement, the arrows will shade toward each other, and so it'll be very easy to tell it's everything between these numbers, and I'll just shade everything in between those two boundaries and be careful which one should be open, close, open or closed circles. And then a lot of times the or statements will shade away from each other, but not every time. So it is important to understand what happens if their arrows are going in the same direction, or to the right or to the left. So we'll interpret a little bit of that as well. But let's just practice just the concept of the and or the or statement. Okay, so you say, let's say we'll look at this example. A number u is less than 7, and, that's our key word here, and greater than 3. Okay, so let's go ahead and translate that to some inequalities. We can say, all right, so I want u to be less than 7, and also I want u to be greater than 3. Now you could leave it like this with the word and in between. Or once we realize, well, I want everything greater, if I put my number line down here, for example, if I want everything greater than 3, I know that would be in this direction, and everything less than 7 would be in this direction. If it's an and statement, I just want everything in between. So I know my graph is going to be right in here. I could also write this as a continuous compound inequality and just say you kind of rotate this one. I know we talked so much about the variable being on the left, but this is one of the exceptions, is if you're going to write it all together. So I could rotate this one and say I want all the u's that are greater than 3 and less than 7. So basically I want everything between 3 and 7. And so when I go to finalize that, neither of those have the or equal to bar, so I'm going to leave those open, but my solution is everything here. Now, what I want you to notice is each individual one had a longer solution, right? So if I had just graphed the u's that are less than 7, that would have been like everything in this direction. And if I had just graphed all the u's that were greater than 3, that would be everything in that direction, okay? But since this is an and statement, my final answer is just the space or the section where it is true for both. So it has to be true for both in an and statement. So this is then our final solution right here, just everything in between 3 and 7, not including them. So that would be the final solution. Even though each individual one has a longer, right, it goes on forever in both directions, I just want this overlapping section that is true for both. Let's compare that to this next one, which is an or statement. A number d is less than -2 or greater than or equal to 2. So let's go ahead and lay that out as an inequality, first of all. So d is less than -2 or d is greater than or equal to +2. Okay. Now, or statements will never be written together. That is only in an and statement. So if it is an or statement, it will always be separated, and the word or should always be in between them. So these do not get blended together like an and statement can. All right, and then let's go ahead again. Now, this one's a little different. Honestly, the or statement, since we're not looking specifically at where they overlap, I just want to make sure it's true for one or the other. Then I want every single answer that makes at least one of these true. And so all you're really doing at this point is graphing each one of these, but just on the same number line. To be honest, that's all there is. Okay, so in an or statement, I go ahead and I'm going to make my number line here. And then I would just graph both inequalities on the same number line. So I want every single d that is less than -2. So that's open circle and to the left. Or any d that is greater than or equal to 2. And as long as it makes at least one of those true, then I want to make sure I include it. So all of these numbers work and all of these numbers work because they're true in at least one of those. So that or statement just basically means give me all of the solutions that are true here or there. I don't need them to overlap. I don't need to narrow it down. It's just all of those values right there. So you're really just graphing each one, but on the same number line, and saying, hey, anything that either makes this true or that true is good with us. Okay. All right, so let's go ahead and try one more. Let's try number 4 here. It says a number C is more than -4, or, again, that's our key word here, at most -6 1/2. So let's go ahead and write that out. C is more than -4, so that is greater than -4, or at most -6 1/2. So that means at most means less than or equal to that -6 1/2. And since this is an or statement, we just graph each one of these on the same number line. Okay. Now these are both negatives, so I'm going to focus my number line here on the negatives, like that. And so let's see which values make this true. I want all the C's that are greater than -4. So that means open circle and greater than. And then all of the C's that are less than or equal to 6 1/2. So 6 1/2 would be like right about here. Okay. And I would include it, and I would want everything less than. So basically, it would look something like that. Okay. All right. So let's talk about solving compound inequalities now that we know what those are. It says you can solve a compound inequality by solving two inequalities separately. Okay. When a compound inequality with the and statement is written as a single inequality, you can solve that inequality by performing those same inverse operations on all sides, and that's really the big difference here. So on all sides of the expression. So of the expression, not on. Okay, but this is the key word right here. So this kind of looks funny the first time you try it, but then it's like, oh, I can kind of solve two equations at the same time, and that's what I'm going to show you next. So number 5 is a really good example of this. We right away know that this is an and statement. Even though the word and is not in there, we know this is an and statement because this is all together. Like we have two, this is truly what a compound inequality typically looks like. So we've got an inequality on the left and on the right, and you've got this work in the middle. Now, typically, if we were to solve this individually, and you can still solve an individual, if you wanted to separate it out and solve each one independently, you can. But I'm going to show you in an and statement where it's written, as a single inequality altogether, like this guy, you can do it all together at the same time. So I want y'all to think about this real quick. If I were solving just this left side, and I wanted to solve this for x, then to isolate x, I would have to add 3 on both sides, right? So on this side, I would have to do like +3 here and +3 there. If I were solving this side independently, I would also have to add 3 on both sides to get x by itself. I would add 3 right here and right there. So when it's written as a single one, you can just solve the whole thing together as long as you do that inverse operation on all 3 sides, right? We always say on both sides, but in this case, there's 1, 2, 3 parts to this. There's the left part, the middle, and then the right. So the moral of the story is if it's written together, you can go ahead and solve it all at the same time, as long as you don't forget to add that 3 on both sides, on all sides, right? Like if I did this one by myself, we just agreed, I would have to add 3. And if I did this one by myself, I know I would have to add 3. So I'm just adding 3 all in the same step. Okay, and then let's see what that result is. So on this far left, 4 plus 3 is 7. In the middle, this cancels, and we just have x. And on the right, we've got 7 plus 3, which is 10. So that's the solution to our compound inequality. It's all the x's that are greater than 7 and less than or equal to 10. And so I only want to graph the values that make both of those true. I only want to graph the values where x is in between 7 and 10 and not including 7. Okay? So now I can go ahead and graph this. Go ahead and to graph it, I'm going to put a circle on each of those boundaries, so on the 7 and on the 10. The 10 is included, so I'll fill that one in. The 7 was not, so I'll leave that open. And I want all the x's that are in between, that are greater than 7 and also less than 10, so it's just everything right in here in the middle in between. And that's our graph. That's the solution, and that is our graph. All right, let's take a look at number 6, because this one does get interesting. It's still an and statement. It's still written all together. And so I can solve it. And like I said before, if you were solving each one of these individually, you would do the exact same thing. You would divide by -5 on both sides. You would divide by -5 on both sides to isolate the g. So you are welcome to do that all together. And just make sure you divide by -5 on all of these sides. Okay. However, hopefully kind of your spidey sense is tingling here. You're like, oh, wait a minute. We just talked about this, right? So when we divide by a negative, yes, this is going to cancel. All of those good things are going to happen. But any time when we're dealing with inequalities that we divide or multiply by a negative, don't forget we have to flip that sign, right? So as I bring down these new solutions, both of these are going to have to flip, right? Just like I would have flipped them if I had done each one individually. So 15 divided by -5 is -3. I'm going to have a less than or equal to sign here. Then in the middle, it's just going to be the g. This guy's also going to flip because I also divided by a negative over here. And this is a +2. So make sure you flip the sign if you multiply or divide by a negative on all sides. And that is our solution. And then it looks like it's all the g's that are greater than or equal to -3, and also less than or equal to 2. So everything between those. Let's go ahead and finish this out. We've got -1, -2, -3, and then 1, 2, 3. And then our boundaries, that's where I'm going to put my circles. I have a circle on -3 and on +2. Both of those are included, so I'm going to fill them in. And I want all the g's that are in between, all the g's that are greater than this -3 and less than this 2, so it's everything in between there. Just like that. Okay? In an or statement, there is no option for solving it all together. And in fact, a lot of times in an or statement, the equations are not even the same. So pay attention to where this or is, because that's separating the two inequalities. And if you notice, the work that I would do here to get z alone, which would be a -4 to get rid of that, is not the same work that I would do on this inequality that is being multiplied by -3. So in the or statements, unless they're identical, but most of the time they're not, we don't have the option of just like, oh, I'll just do the same thing on all sides. And really, again, I'm going to say it one more time, or statements are just two inequalities being solved, but just graphed on the same number line. Okay, so let's try number 7 here. On number 7, I'm just going to treat each one of these independently. So I'll start with the one on the left. Here's my variable. They added 4. Everything is simplified. We're ready to solve, so I'll just get rid of the 4 with a -4. And that'll cancel this. And that'll leave me with z is less than -2. And then on the other side, I've got being multiplied by a -3, so I need to divide by a -3. And again, if we divide by a negative, ding, 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 don't forget to flip the sign. So this becomes z is greater than, and then I have my 9. Okay? And this is an or statement, so I want all of the values that are either less than -2 or greater than 9. And as long as it makes at least one of those true, I want to include it. So it's basically everything that makes one or the other. We're just going to graph both of these on the same number line is really the moral of the story. And just for the sake of space, I'm going to go ahead and go by 2's here. Okay, and so I want all the z's that are less than -2, so open circle and to the left, or anything that is greater than 9, so 9 would be right in here, greater than 9. That would be our graph, and that's all we would have to worry about. Okay. All right, we are going to leave 9 and 10 as our quick warm-ups in class. We'll do those together, and that's your lesson on compound inequalities.